Good day, everyone. So our topic for today is about stoichiometry. Under these are the topics mole concept and molar mass of elements, molar mass of compounds, percent composition of compounds, and empirical and molecular formula. I am Dr. Erwin R. Abrencilio. So let us first have some discussion on the learning outcomes for this presentation. So first is at the end of the session, you are expected to explain the mole concept. Second, determine the formula or molecular weights and the percentage composition of a compound given its formula. And determine the empirical and molecular formula of a compound. So let us now begin with the first lesson, which is mole concept and molar mass of elements. So the identity of a substance is defined not only by the types of atoms or ions it contains, but by the quantity of each type of atom or ion. Of course, you have to recall the difference between an atom and an ion. However, the identity is not just defined by as mentioned, by the types of atoms or ions that it contains, but by the quantity of each type of atom or ion. So how many atoms are there in a certain formula, or how many ions? So for example, let us take water and hydrogen peroxide. So water, it has a chemical formula of H2O, and hydrogen peroxide with a chemical formula of H2O2. They are alike in that their respective molecules are composed of hydrogen and oxygen atoms. However, they differ in the number of hydrogen and oxygen. Though both are composed of hydrogen and oxygen, they differ when it comes with the number of atoms of each element in their formula. So for example, as mentioned, because a hydrogen peroxide molecule contains two oxygen atoms as opposed to the water molecule, which has only one, the two substances exhibit very different properties. So it's just a small amount, one atom difference on the number of oxygen. However, water is far different from hydrogen peroxide when it comes with their chemical and physical properties. So how are we going to define a mole? So a mole is defined as the amount of substance containing the same number of discrete entities. The discrete entities may be atoms, molecules, and ions, and others, as the number of atoms in a sample of pure 12 carbon weighing exactly 12 grams. So our basis for this is carbon atom. So one Latin connotation of the word mole is large mass or bulk, which is consistent with its use as the name for this unit. So the mole provides a link between an easily measured macroscopic property like as bulk mass and an extremely important fundamental property, number of atoms, molecules, and so forth. So we are going to discuss more of that in the preceding slides. So I have here the formula for the number of moles. So for you to be able to get the number of moles, you have to understand first this formula. So N symbolizes mole, M, small letter M, symbolizes the mass of the sample based on the given problem, and capital letter M is the molar mass of the sample. So the number of entities composing a mole has been experimentally determined to be 6.022,14179 times 10 to the power of 23, a fundamental constant named Avogadro's number. So it is in honor of Amedeo Avogadro. So this constant is properly reported with an explicit unit of per mole. So it can be rounded off to 6.022 times the 10 to the 23rd power per mole. So again, that depends upon on the entities that we are looking for. It could be atoms, ions, molecules, and so on. So consistent with its definition as an amount unit, a mole of any element contains the same number of atoms as one mole of any other element. So the masses of one mole of different elements, however, are different. So since the masses of the individual atoms are drastically different, of course, we will understand this more in our problem solving in the next slides. So let us define now molar mass. So molar mass of an element, or it could also be the molar mass of a compound, is the mass in grams of one mole of that substance, a property expressed in units of grams per mole. So for example, 5 gram per mole, 15 gram per mole, 29.9 per mole, a gram per mole. So that's the molar mass. So if it is a molar mass of an element, you will only get the molar mass of an element alone. If it is a molar mass of a compound, it should be the combination of the molar mass of elements together with their number of atoms for you to be able to get the total molar mass of the compound. Of course, I will explain that to you later on. So let us look into this example number 1. So let us have first the problem. So according to the nutritional guidelines from the U.S. Department of Agriculture, the estimated average requirement for dietary potassium is 4.7 grams. What is the estimated average requirement of potassium in mole? So this is our problem now. So for you to be guided properly in solving problems like this or any problem in science, so it's better to write it this way. So first is you have to write the given and then the solution. So under the solution, you have to write the formula. So for the given, you have to analyze first what the problem is. So we have here the mass of the sample, which is 4.7 grams. You may likewise write the symbol for potassium, which is letter K, or 4.7 gram K, or 4.7 grams. It's up to you. So if you're going to look into the periodic table of elements, you can be able to get the atomic weight of potassium, which is equivalent to 39.10. You may include the 2 decimal places. You may include all the numbers there, or you may likewise just round it up to the whole number. However, it may or may not have an effect on the number of moles that you are going to solve. So for the molar, based on that, on the atomic weight or atomic mass, you can be able to get the molar mass. It is the same. All you have to do is to change the unit into gram per mole. So molar mass is 39.10 gram per mole. So that's our given. So based on the given, you can now use the formula as part of your step under solution. So the formula is N is equal to M, or mass divided by molar mass. So based on that, so you can write 4.7 gram, which is the mass of the sample, divided by 39.10. So of course, you have to invert mole. Mole will be written on top and gram will be written at the bottom. So it is written that way because, of course, you have to cancel the units for grams so that at the end, you'll be able to get mole as your final unit since you are looking for the number of mole. So that's why in the illustration, there is cancellation of grams. So 4.7 divided by 39.10, you can be able to get 0.12 mole of potassium. So that's our example number 1. So let us now proceed to example number 2. So copper commonly used to fabricate electrical wire. I'm sorry for the typographical error. How many copper atoms are in 5 grams of copper wire? So that's copper wire. So given is mass of the sample, which is equal to 5 grams based on the given. And the molar mass of copper, if you're going to look at the periodic table, the symbols capital C, small letter u, or Cu. So it is equivalent to 63.55 gram per mole. So same thing. However, we are looking for the number of atoms. So unlike a while ago in the example number 1, we are looking for the number of mole. So in the number of mole, it is solved as is. No need to multiply that to the Avogadro's number. However, in example number 2, we are looking for the number of atoms. So that's why the formula is a bit different. But it's almost the same in a sense that all you have to do is to multiply it with the number, with the Avogadro's number. Now, um, we substitute 5.0 gram for the mass of the sample, which is the mass of copper, divide by 63.55, which is the molar mass, and then cancel the grams. And then for solving it for the number of atoms, all you have to do is to multiply it with the Avogadro's number of 6.022 times 10 to the 23rd atoms per mole. So again, that depends on the given. Since we're looking for the number of atoms, we use the term atoms. So with that, you can be able to cancel mole. And then if you are going to solve that, make sure to use scientific calculator, the legit ones, not the one from your cell phone. So we have 5.0 times 6.022 times 10 to the 23rd atoms divided by 63.55. With that, you can be able to get an answer of 4.74 times 10 to the 22 atoms of copper. So that's the second example. Let's now proceed to the third example. So a liter of air contains 9.2 times 10 to the negative 4 mole of argon. So the symbol for argon is Ar. What is the mass of Ar in the liter of air? In a liter of air. So with that, we can be able to write the given. The given is the number of mole of the sample, which is 9.2 times 10 to the negative 4. Meanwhile, the molar mass of argon is 39.95 gram per mole. So you can now substitute the given. Okay, so we have here 9.2 times 10 to the negative 4 mole of argon. So divide by, multiplied by 39.95 gram per mole. So notice the difference with the positioning of the given molar mass. Since the given is in mole, so we have to cancel mole for us to be able to get mass. So it is 9.2 times 10 to the negative 4 times 39.95 grams is equal to 0.037 grams of argon. So I hope that you are getting the idea now. So let us now talk about the molar mass of a compound. So each ion or atom has a particular mass, as of course, we all know that. So similarly, each mole of a given pure substance also has a definite mass. The mass of 1 mole of an atom of a pure element in grams is equivalent to the atomic mass of that element in atomic mass units or AMU, or in grams per mole or gram per mole. So although mass can be expressed as both as AMU and gram per mole is the most useful system of units for laboratory chemistry. Of course, we can be able to solve other problems in chemistry if we are going to use that symbol gram per mole instead of using AMU or atomic mass unit. So the molar mass is the mass of a given substance divided by the amount of that substance measured in gram per mole. For example, the atomic mass of titanium is 47.88 AMU or 47.88 gram per mole. So in 47.88 grams of titanium, there's 1 mole of 6.022 times 10 to the 23rd titanium atoms. That's the number of atoms for titanium. So the characteristic molar mass of an element is simply the atomic mass in gram per mole. So however, molar mass can also be calculated by multiplying the atomic mass in AMU by the molar mass constant 1 gram per mole, so that you can be able to get the unit gram per mole. So to calculate the molar mass of a compound with multiple atoms, Sum all the atomic mass of the constituent atom. So just like this one. So example number 4, for example, the molar mass of NaCl can be calculated for finding the atomic mass of sodium, which is 22.99 gram per mole, and the atomic mass of chlorine, which is 35.45 gram per mole, and combining them. So the molar mass of NaCl is 58.44 gram per mole. So we have here NaCl. If you're going to analyze it, it has no subscript at all. So automatically, their value is 1. So Na is 1, Cl is also 1, multiplied by their atomic mass, which is 22.99 for sodium and 35.45 for chlorine. So at the end of it, you can be able to get 22.99 and 35.45. So if you're going to add that, that is 58.44 gram per mole. So that's the molar mass of a compound. The molar mass, again, of a compound is the combination of the molar mass of each member atom or each member element. So let us move on to the next example. So our body synthesize protein from amino acids. So one of these amino acids is glycine, which has the molecular formula of C2H5O2N. How many moles of glycine molecules are contained in 28.35 grams of glycine? So with that, you can actually use a table if you are comfortable with it. So our first step is to write the table in a manner like this, the one that you are seeing on the slide. And then you write the number of atom for each element. So see, there are 2 atom, and then H is 5, and O is 2, and N is 1. Then multiplying that with the molar mass of the gram per mole, so that at the end you can be able to get the molar mass or molecular mass. So you have there 75.07 gram per mole. So since you have now the given, you can now move on to the other steps. Okay, so we have here 28.35 gram of glycine, and the molar mass is 75.07 gram per mole of glycine. So you can be able to cancel the gram unit, and you can be able to get the mole per glycine, which is 0.378. All right. So let us now move on to the next, which is percent composition of compounds. So percent composition is very simple. So it tells you by mass what percent of each element is present in a compound. So a chemical compound, as we all know, is the combination of 2 or more elements. If you're studying a chemical compound, you may want to find the percent composition of a certain element within that chemical compound. So for you to be able to get or to solve percent composition, you have to, of course, you have to multiply it by 100. That's the key there. No, whatever answer there are, so multiply it by 100 so that you can be able to get the percent. So if you want to know the percent composition of the elements in a compound, sorry for the typo, follow these steps. So find the molar mass of the elements in the compound in grams per mole. So that's the first step. Find the molecular mass of the entire compound. Divide the component's molar mass by the intermolecular mass, and you will now have a number of 0 to 1. Multiply it by 100 to get percent composition. So just like this one. Sorry, it's quite blurred. So we have here the compound PCl5 or phosphorus pentachloride. So how are we going to get the percent? So first, find the molar mass of all elements in the compound. So molar mass for phosphorus is 30.974 and chlorine is 35.453. However, there are 5 atoms in chlorine, so 35.453 multiplied by 5 plus 30.974, you'll be able to get 177.265 grams. Now, since you have now the molar mass, so you have to get the molecular mass. So PCl5 is equal to 30.974 plus 177.265. So you'll be able to get 208.239 grams. So you now have the molar mass of the compound. So divide each molar mass by the molecular mass and multiply by 100. So the total a while ago for molecular mass is 208.239. So we have to divide 30.974 of phosphorus times 100, you'll be able to get 14.87%. And for chlorine, it's the 177.265 gram. And then you'll be able to divide by 28.239 grams times 100. You can be able to get 85.13%. So therefore, phosphorus pentachloride is 14.87% phosphorus and 85.13 chlorine by mass. So this is the last part of our discussion. So we have here the empirical and molecular formula. Of course, these are chemical formulas that we usually use in a chemistry subjects or chemistry laboratory. So molecular formulas tell you how many atoms of each element are in a compound, and empirical formulas tell you the simplest or most reduced range of elements in a compound. So both are chemical formula. One is actual, which is molecular formula, and one is reduced, which is the empirical formula. So if a compound's molecular formula cannot be reduced anymore, then the empirical formula is the same as a molecular formula. So once known, the molecular formula can be calculated from the empirical formula. So an empirical formula tells us the relative ratios of different atoms in a compound. The ratios hold true on the molar level as well. So for example, H2O is composed of 2 atoms of hydrogen and 1 atom of oxygen. So likewise, 1 mole of H2O is composed of 2.0 mole of hydrogen and 1.0 mole of oxygen. So we can also work backwards from molar ratios. Since if we know the molar amounts of each element in a compound, we can determine the empirical formula. So let's say we had a 100-gram sample of this compound. The sample would there is 73.9 grams of mercury, 26.1 grams of chlorine, and how many moles of each atom do the masses represent? So first for mercury, we have 73.9 grams, which is the given. And the molar mass of mercury is 200.59 grams. So 73 gram divided by 200.59 gram is 0.368 mole. For chlorine, same step. So the given mass is 26.1 grams. So you have to multiply it with the 35.45 grams of the molar mass of chlorine. So at the end of it, you'll be able to get 0.736 mole. And if you are going to get the molar ratio of the two, so 0.736 mole of Cl divided by 0.0368 mole of mercury is equal to 2.0. So with that, we know that we have twice as many mole of Cl and Hg. The empirical formula would thus be HgCl2. So of course, you have to write first the cation, which is Hg or mercury, and Cl2 or chlorine as the one that should be written next. So we have example number 8. So this is example about vitamin C. So vitamin C contains 40.92%, 4.15% H, and 54.50 O by mass. So experimentally determine molecular mass is 176 AMU. What is the empirical and molecular formula for ascorbic acid? So consider the following: 40.92 grams of vitamin of C of carbon, and 4.58 grams of H, hydrogen, and 54.50 grams of oxygen. So in this case, we multiply it by the, we use the formula for molar mass. At the end of it, you'll be able to get 3.407 mole of carbon, 4.544 mole of nitrogen and 3.406 mole of oxygen. So determine the next thing is to determine the simplest whole number ratio by dividing the smallest molar amount. So the smaller molar amount is 3.406. So divide with the smallest molar amount, you'll be able to get 1.0. However, that's not yet the final answer, because if you're going to look at it, there are decimal places there on H, which is supposedly 1.3333. Okay, so the solution there is to multiply it by a number that will make it as an integer or whole number. So since H is 1.3333, so the number that we could use is 3. So you have to multiply it by this number. So 1.0 times 3 is 3. For carbon, for oxygen is the same. However, for hydrogen, we have 1.33. So when you multiply it by 3, you'll be able to get 4.0 or 4. So with that, we can say that the empirical formula for ascorbic acid is C3H4O3. So this is another example or continuation of that. So how about the chemical formula? So we are told that the experimentally determined molecular mass is 176 AMU. So that is already given. So what is the molecular mass of our empirical formula? So multiply it by the number of atoms. So 3 times 12.011 plus 4 times 1.008 plus 3 times 15.99, you'll be able to get 88.062 AMU. So you have to use that 88.062 AMU to divide with the given 176 AMU. Then you'll be able to get 2.0. So the 2.0 will be the one to be used in our molecular formula from empirical formula. So a while ago, our empirical formula is C3H4O3, but it can become a C6H806 as our molecular formula, since I use 2 to multiply the entire chemical formula. Right, so that ends my discussion. So I hope that you now have an understanding of the given topic. Thank you so much, everyone.